Okay, welcome back, Bio. We're going to finish up section 1 finally today. It's a little bit of a longer section. Again, talking about what is science. And if you remember from last time, we were talking about, again, the scientific method and the examples of a salt marsh grass, talking about how the scientists noticed that one group in one area grew taller than another group in the other. And we talked about how to set up a controlled experiment where only one variable is changed at a time, and we talked about having a control group, which is again the group that remains the same. So again, when we have an experiment, we leave one group always the same, and then our other group, we only have one variable that changes to make sure we know what exactly is causing our results. So we're going to continue right on where we left off. The other video was running a little long, so that's why I go ahead and stopped it to start our next one. So we're continuing on with our example of the salt marsh grasses. So we just got done talking about, again, having our experiment divided into two groups, our control and experimental. So in our example, our researchers, they selected similar plots of marsh grass. All plots had similar plant density, soil type, input of fresh water, and height above average tide level. So the plots were divided into control and experimental groups. So they found an area where everything was pretty much the same throughout. So this is an area where if they just added one different thing, they'd be able to tell what was causing that change. So the researchers added nitrogen fertilizer, which is again our independent variable, to the experimental plots. Then they observed the growth of the marsh grass, which is our, holy cow, I am stuttering very bad. Then they observed the growth of marsh grass, the dependent variable, in both experimental and control plots. Wow, that was the worst paragraph I've ever had. So basically, in my own words, what just happened there is they divided up their plot of ground into two sections. In one section, the experimental group, they added more nitrogen fertilizer. In the other group, they did not add any nitrogen whatsoever. So the only nitrogen that was added was whatever is there naturally. So one group, again, the control group is, when we think of controlled, it means it is something that is unchanged. It is something where everything is the same. Where our experimental group, we're changing one factor, which again, in this case, was the nitrogen. So then scientists will record their observations, gathering information called data. So that's a big word, information that is gathered during experiments called data. So there are two main types of data, quantitative versus qualitative. When we think of quantitative data, that's data that is obtained by counting. So data obtained by counting or measuring is quantitative. So that would be in the experimental group, the marsh grass grew to 15 meters tall. Again, that's gigantic, but again, that would be an example of quantitative data. It's something that you can physically count. So the example could be the number of plants there were, the size, the growth rates. Again, quantitative, when you quantify something in math class, that means you count it. It has to deal with actual numbers. So then on the flip side of that, qualitative data are descriptive, and they involve characteristics that cannot easily or usually be counted. So knowing the difference between quantitative and qualitative, being more descriptive, is a very important thing. So in our marsh grass, man, I struggle saying marsh grass experiment, it might include notes about foreign objects in the plots, or whether the grass was growing uprights or sideways. Again, there's no way to measure how sideways the grass is growing, or if, let's say, some teenagers decided to throw a tire in there. That would be more qualitative data that they would have to take into account. So once they have all their data collected, or actually kind of to go along with that, the scientists have to choose appropriate tools for collecting and analyzing that data. So again, we're not going to use a thermometer to measure how tall our grass grew. We're going to use a meter stick of some kind. And tools can include simple devices such as the meter sticks. They can be sophisticated equipment such as machines that measure the nitrogen content. So within that plot, we can actually find machines that tell us how much nitrogen is present before we get there. And then charts and graphs help us organize our data. So again, this graph shows how the height changed over time. So over a certain amount of weeks, this control group, which again is the one that is unchanged, it grew, and you can see that in the blue line. However, you can see the one The 1N, meaning the nitrogen that was added, obviously increased the height of our grasses. So the red line obviously shows height over here on the left is much greater in our experimental group compared to our control group. So in the past, we would record that data by hand, we'd draw out a graph, and it might take us a little bit longer. Today, however, we can enter data into computers, into things like Microsoft Excel, which will make up that graph almost instantly for us, and will make it a lot easier. So that is kind of the basis of, again, when we're doing our research, how we present it, collecting the data. However, when we are collecting our data, there always are sources of errors. So researchers do their best to be careful to avoid errors in data collection and analysis. So tools used to measure the size and weight of marsh grasses, for example, have limited accuracy. So nothing that we have, again, readily available to us at the time can measure the exact height of a piece of marsh grass. There's obviously, with the wind blowing, again, with the top of it not being completely level off, there's always going to be some mistakes that can occur. So data analysis and sample size must be chosen carefully. So the larger the sample size, the more reliably researchers can analyze variation and evaluate the differences between our groups. So what that means is, if we have more to choose from, that means there's less likely for some type of anomaly to occur. So let's just say that within our control group, there's just a random strain that grows to be giant in size. It's a mutation that you don't ever find. That might skew our results, so we kind of have to keep that in when we have a source of error. But if we have a giant patch and we only see that one giant plant sticking out, that's going to tell us, okay, that just must be a fluke. We can't really consider that too heavily when we're factoring our results. So once we, again, take into account our error, when we're taking our measurements, our last step is to draw some type of conclusion. So we use our data as evidence to support, to refute, or to go back and revise our hypothesis that's being tested, and then to draw a valid conclusion. So if your hypothesis is wrong, that's no big deal. You just need to go back and revise it. Again, the only way it could be wrong is if you just stop there and you don't continue on your scientific work. And again, analysis showed that our marsh grasses grew taller than controls by adding nitrogen. So that supports our hypothesis that was originally made. So then we draw our conclusion. It says new data may indicate that the researchers have the right general idea, but maybe they're wrong about a few particulars. In that case, the original hypothesis is reevaluated and revised, and new predictions are made, and new experiments are designed. And our hypothesis may have to be revised and experiments redone several times before a final hypothesis is supported and conclusions can be drawn. So again, don't write this all down. The main gist of this is saying that once we draw a conclusion, we can't accept that to be a fact all the time. We can say that for now that is correct with the available information that we have, but I guarantee in about 10 years, almost any experiment that's going on now with living things, there's going to be new observations added, new conclusions can be drawn, and again, the things that you learn in my class this year are probably going to be way different than the thing your kids are going to end up learning. And our next, to end up here, talks about that we don't have always have the capability to do an experiment. Again, don't worry about writing this all down. Our main thing would be if we're researching animals and we want to see how an animal naturally behaves, we're not going to go in, we're not going to change and manipulate the animal. We just kind of have to follow it, record what we see, and kind of do the data based off of that. So that is it for section 1. Let me know if you have any questions.